Hey guys, day 6. We made it to a new week. We made it to Thanksgiving week, my favorite holiday, Thanksgiving, aka the best holiday. If you disagree, well, that's okay. You're just wrong, but it's okay to be wrong sometimes. But, guys, I thought we'd start off with everybody's favorites. Why not start this great holiday week off with triangle proofs? There's our word. We love it. We love proofs in this household. I'm gonna draw a heart. Hopefully, it doesn't look like a butt. And so, guys, the key here with these proofs, we know it's all about knowing what topic you're talking about. So we're going to be talking about the postulates we learned last Friday on day 5. These postulates right here, side, angle, side. All these postulates are going to be key, as well as some throwbacks, vertical angles, midpoints, angle bisectors, things like that. And then, of course, it all comes back to proving corresponding parts of congruent triangles are congruent, aka C, P, C, T, C. And so remember, guys, when we deal with a proof, like number 1 here, you want to look at what we're given. So we know we're dealing with triangles. Nah, crap, right? Based off the topic in the chapter. But here's the big thing. Look what we're trying to prove. ABD is congruent to CDB. Okay. So in other words, we're trying to prove that these two triangles are congruent. Well, we know that's going to come back to this right here. This is going to come back to one of these right here. So we look and we say, okay, what are we given? Here's the thing. Always start right here. AD is congruent to BC. Okay. This side is congruent to that side. Also, DC, Washington, is congruent to AB. Okay. So that's a good start. That's what they gave us. Well, now, I look and I say, okay, what's the last really remaining piece here that we can pull based off this picture and what we've been given? Wait a minute. If this side and this side are the same, this side and this side are the same, I'm thinking side eventually is going to get us there. The question is, we have to prove that this side is the same for both these triangles, because both these triangles share it. So in other words, we need to prove that side DB is equal to, so DB for this triangle is equal to, DB for this triangle. So what property proves that something equals itself? We're going to throw it all the way back to chapter 2. Some of you guys know it. That's the reflexive property. If you remembered that, shouts out to you guys if you remember that. That's awesome. And so now, how can we prove that ABD, this triangle, is congruent to that triangle? Well, all 3 sides are congruent. So with some side, triple S's, like a snake. Sorry, I apologize. That was really lame. Let's do a couple more, guys, and then I'm going to try giving you a chance to work on some. So again, I look and I say, okay, what are we given? XZ, congruent to ZB. YZ, congruent to ZA. And I look and I say, what else am I seeing here that's probably going to come into play? Ooh, angle 2 and angle 4. We're going to have some vertical angles up in here. That means we're going to have a theorem and a definition. We're going to have both these at some point, most likely. So let's get into it. And it looks like we're trying to prove that this triangle is going to be equal to this triangle. So it's going to be one of these to end it up here. We know it's going to be one of these at the very end. But in the meantime, we're given that. We're told 2 and 4, hey, definition of vertical angles. But what does it mean if they are vertical angles? That means they're equal to each other. That's the good old vertical angle theorem. And then because angle 2 and angle 4 are congruent, that means we have a side, an angle, and a side. Side, angle, side. So hey, we just answered our last step here. We can use side, angle, side to prove that these two triangles are congruent. So hopefully you're with me so far, guys. If not, again, remember, you have several ways to contact me. You can reach me through Remind. You can reach me through email. We can do a Google Meets. I want to help you guys out. But before we get to that, we're going to be changing the game a little bit on this one. Okay? Nothing too crazy. We're given some angles. 3 equals 4. So this angle are congruent. And 1 and 2 are congruent. Okay, little diagonal angle action. Now, they actually go ahead and tell us, let me adjust my camera, they actually go ahead and tell us that MO is going to equal MO. In other words, these two triangles share the same side here. N opens up to it, P opens up to it. Okay, so we know we've got, looks like angle, side, angle. It's kind of what I'm thinking here is going to be definitely our option eventually. We're not quite there yet, angle, side, angle, because we need to make sure we know which triangle is equal to which. So M-O-N. What's that going to be equal to? Remember, order matters. I cannot stress that enough. Order matters here. So we know angle M starts here. It looks like the angle that lines up with it would be 1 and 2 here, and 2 belongs to O. So we've got O. And then where do we go to next? Well, it looks like on this triangle we go from M to O and then to N. So we go across this long piece here. So we're going to go the exact opposite way. O, okay, to M. And then it went to N over here. So we go across and we're going to go down to P. O and P. And we can say these two triangles are congruent. Why? Voice crack. Why? Because of angle, side, angle. But wait, that wasn't what we were trying to prove. We were trying to prove that angle P, this angle, equals this angle. So wait a minute, how are we going to do that? We already proved the whole triangle equals the other triangle. How do we prove this specific piece now is equal to a specific piece? Guys, that's where this comes back. We've proven that the triangles are congruent. That means their corresponding parts are going to be congruent as well. So I go down here and I say, hey, now that we've proven both triangles are equal, we know these two pieces are equal thanks to CP, CTC. And guys, anytime you have the whole is equal leading to parts equal, anytime you take the whole, say these are equal, and then say because of that their parts are equal, that is always CP-CTC. That is the cycle right there. So I'm going to let you guys, we're going to flip over to page 2, and I'm going to let you guys try page 2. See what you guys can do solo on this one. I believe in you. You guys are my proof masters. I've been so proud of you. I'm going to see if you guys can take both 4 and 5 the whole way through. So give me your best shot on these guys. Okay, spanning back from the last one, we know that we're trying to prove that two pieces of different triangles are equal. That we know it's going to end with CP-CTC. If we're trying to prove these two pieces, and we see that especially down here, NKJ, we know we're going to try to prove that that's equal to another triangle. But which triangle? Well, it looks like we're involving N and M. So here is the first triangle we got, NKJ. So 1, 2, 3. Okay. And we're saying angle 4 and angle 5 are vertical. Therefore, those are going to be equal. So we're dealing with this triangle we see. 4 and 5 are equal. So we also know that NM is going to be the same amount as NK. Thanks to the definition of a segment bisector, cuts these into equal pieces. So NKJ, N to K, that's going to be the same thing as N to M And then it looks like we're involving angle 1 here as well. So we'll go to L and then back to N. Okay. So we can say these two triangles are the same, and why is that? Well, if this is an angle, if this is a segment bisector, we're also told JN is the same thing as NL. So these pieces are the same. So it looks like we've got also, of course, yeah, this piece is the same. Looks like we've got side, angle, side. Side, angle, side. And so that's how we can prove these triangles are corresponding. We see these sides are the same, these angles are the same, and these sides are the same. And from there, of course, like we said at the beginning, CP/CTC is going to get us through. Whenever we've proven the triangles are equal, pretty easy to prove their pieces are equal. Number 5, very similar, except this time we're dealing not with a segment bisector. Looks like we're dealing with midpoint. So that's going to be a topic right there, is going to be midpoint. Also, once again, looks like we're going to have some vertical angles. So that's going to come into play too. So first off, if C is the midpoint, we're told angle 1 is going to be congruent to angle 6. That's going to be big. Now we're told AC, A to C, is the same thing as C to E. So this side and this side are congruent. And how can we say that? Well, it came from words to math. That's a straight up definition of a midpoint. We got the definition. That's a great way to write midpoint there. Midpoint. Now we switch gears and we say, hey, we can prove that 2 and 5 are going to be equal because they're vertical angles. That's just based straight off the definition. And because of that, that leads into 2 and 5 being equal based off the vertical angle theorem. So look at what we have right now, guys. Looks like we've got angle, side, angle. Angle, side, angle. And I'm thinking if A to B to C, we know that's going to be A to B to C. Now notice, we never hit this side over here until we come all the way back. A to B to C. So then if we start at D, we wouldn't start at D. We would start at E because we need to only hit this on our way back from the middle. A to B to C, back there. So E to D to C, back there when we hit that. So we're looking at E to D to C. And we said that's going to be angle, side, angle. And of course, we can now say AB and DE are going to be congruent because of CP/CTC. We love it. Yeah. So we just have one problem left, guys, and we're going to be done for the, actually, I'm sorry, we got 2 problems left and we're going to be done. So here's where we get to a little bit tougher one. Check it out. Really going to have to lock in here. PQR is isos. Okay, if we're dealing with isos, we know we have definition of isos triangle, and we have the isos triangle theorem. Now, if you remember, definition has to do with angles. Theorem has to do with sides. And so one thing we're just going to have to be mindful of is that the definition and theorem both end with their conclusion is about congruency. Their conclusion is about congruency when it comes to both of these. So whenever we look, we say, okay, hey, PQR, we are establishing this overall triangle is isos. That means we're also going to say angle 3 is going to be equal to angle 4. Okay, so they gave us both those. Now we're trying to say that PQ, this piece, is going to be equal to QR. And I apologize, I got these backwards. The definition is going to have to do with sides, I'm sorry. And the theorem, some of you guys are probably thinking, wait a minute, I know that's not right. Yeah, the definition is going to have to do with sides. The theorem is going to have to do with the angles. That's my B. So when we go to say PQ is going to be congruent to QR, we're going to make that statement based off Again, both these end with talking about congruency with the definition, which has to do with sides. Definition of isosceles triangles. Now, going along with that, we're going to say, well, what angles project to those if they're equal? Well, angle 5 projects to this side. Angle 6 projects to QR. And so if we're talking angles, we know that's going to be where we bring in the theorem. So we got the isosceles triangle theorem. Let's go. And then finally, here's where we bring it all together very carefully. We're going to say PAQ, P to A to Q. So from the bottom toward the middle and then up to the top is equal to, let's flip it, going to be R, looks like to B, and then up to the same point Q. And we know that because, be careful, we've got angle, side, angle. Angle, side, angle. So some ASA. And if we want to prove any pieces of this triangle are congruent to another piece of the triangle, we've already proven the whole thing is. We can do that just using CPCTC. Every single part of these triangles is going to be congruent. So what I'm going to do now, I'm going to let you guys try this last problem, number 7, before we wrap up with one final thing. So give me your best shot on a little throwback proof about systems of equations. I know some of y'all are going to be ticked because it almost got me too. So first thing you want to think is, oh, I'm going to use the substitution method. Well, the whole substitution method really comes in at the end. What we do at first is we say, hey, wait a minute, x equals 2y plus 7. This is a little bit of a unique situation. We know what x is for both of these. So what we can do is we can say, okay, cut out the middleman. If x equals that and x equals that, then that equals that. That's not substitution. That's my favorite property, transitive. And from there, guys, you're solving a 3-step equation. Subtract the y over, subtract 7 over to get -3, and then from there, here's where we plug that back in, and when we plug something in, a value into a variable, that's when we're talking substitution. A lot of subs here, but these are subtraction, that's substitution. And so what I'd like you guys to do for me, we're going to be checking these hopefully tomorrow, but we're going to flip over, and so your homework, this is on page 4, the bottom half of page 4. It's going to be page 4, page 5. I want to specify this is the bottom of page 4 and page 5. We're going to be doing the practice multiple choice. So that'll be your homework here. Good luck, guys. If you have any questions, reach out to me, and I'll be talking to you very soon.